Hello, students. This is a lecture on glacial and interglacial cycles. So let's get started. There you go. Okay, so this is a graph of Greenland ice core. This is a record of it here. You can see on the left-hand side we have the change in temperature and also the dust in parts per million. And here we have the thousands of years ago. This is also CO2 here in the green. So the one thing to note on this specific graph is that it goes kind of backwards as what you might actually most graphs actually go. So it's going to go backwards in time towards the right instead of the other way, which usually you would have the present time here and then kind of going, backwards. So this way. So kind of, I guess, think about it as going back in time from the left hand side here. So the first thing to notice is what we notice in a lot of other graphs where the CO2 and the temperature have this direct correlation to each other. This we're used to seeing. But what's going on with this dust? You can see the dust here has some peaks. What's interesting about the dust, though, is that it falls right before this temperature peak. So when it's down here at the coldest point, you can see that there's a maximum here in the dust, and then right after that, it's going to have a peak in temperature and CO2. So I'm just kind of pointing that out to you guys. Another thing that's interesting about this graph that I want to point out is that it has very sharp increases and decreases in the temperature. Something's got to be going on here because it is, such a sharp decrease and increase. You'd expect, at least me, maybe before I really knew about carbon and the carbon cycle and CO2, I would kind of maybe expect it to kind of go, more gradually. But there's really quite a bit of a drop off here. So, we're going to kind of go into that a little bit. Let's see. Just another couple things about this graph is that there's quite a bit of time where it's actually below zero, so below freezing. And then obviously it kind of warms up here more towards current time. I'm sorry, this is backwards. See, it warms up during current times. Let's see. And then there's also somewhat of a frequency here every 100,000 years. So there's something going on with that. See if you can think about what might be happening maybe every 100,000 years. So one thing though is, the temperature we use proxies for temperature, we'll use different types of things, tree rings, coral reefs. I teach in my global climate change class that we actually, there's a rodent that actually its urine, actually perfectly preserves fossils, like plant fossils and things like that. And so, and they always go back and use the restroom at the same place. And so it's actually a weird record that we have, going down and, into what's been buried of what has been happening throughout time with plants. But, the CO2 in this specific one here in Greenland, because it's frozen over, they're using ice cores. So here's actually a picture of an ice core. And what's interesting about an ice core is that it actually perfectly preserves these little air bubbles inside of it. So what happens is we can actually evaporate this ice core under a vacuum and then actually take a direct sample of what the actual atmosphere was like at that time. And, it's going to go down and down and down and down because obviously, every winter it'll freeze over, it'll accumulate more. And so, kind of interesting how we have that ability, at least in Greenland. Okay, so what do these ice core layers look like? Kind of interesting here. This is a picture of an actual ice core. This is the GISP2 ice core, which they found, take out of the Greenland summit. It is archived at the National Ice Core Laboratory in Colorado. Now, one thing you can see is that, there's definitely some lines here. And what happens is it's a difference in the size of snow crystals deposited in winter versus summer. right? And so you can obviously during the summer it's not going to have really any ice crystals that will accumulate. Maybe very little depending on what's happening that year. But during the winter it'll definitely there'll be some ice crystals that accumulate. So you can see how you can actually count how many layers there are here, and those layers end up being quite a bit of an accurate idea of what's happening throughout time here. Actually, I'm sorry, like how far back it goes back in time. So this specific one is around 16,000 years ago in the end of the last ice age. So there's about 38. I have 38 years here. This is definitely a typo, but it's going back, quite a bit of time. Or it's actually, I'm sorry, this is 38 years. I don't know why I got confused, but yeah. So this is 38 years that's represented here. Now, this isn't actually the longest or the furthest back the ice cores go. The furthest back is actually in Antarctica. It goes back about 800,000 years. So super cool though. We can actually get direct measurements of what the I'm so tired today. My brain is not working. So what the atmosphere actually looked like at that specific time. Let's see. I want to make sure I'm not forgetting to say anything. Okay, so this is actually, where they'll actually collect these ice cores. And here's what one looks like. It's right here in this little, I don't know, tubey thing here. They can section them off and into different sections, and that way they can transport them, put them into the archive, study them. It's a nice, way of visually also looking at, you can see how far down, when you get close to it. What's going on. Okay, so this one is actually some guy getting a smaller core, because he's only taken like a little sample here of what's come out of, the sample or the drilling that they're doing here. You can see that they store them up here in these really large areas. And then they also have ways of taking larger ones too. And so this one is quite a large one. That way you can have a larger sample for each period of time. I guess you can actually go in there and request a sample. This is not something I've ever done, but I hear this is something you can actually do. Let's see. Okay, you can actually also go to glaciers. This is a great idea here because, what's happening in Antarctica is not going to show you what happened in South America during the same time. So these going into glaciers is going to give you more of a regional information, and can be useful as to like what's happening, why what happened. So like why did it have those really sharp peaks and valleys inside of the well, that was in Greenland, but when you see that in Greenland, then you could say, well, why in the world is that going on? And then you can look at other samples from other areas here. Let's see. Just gives you basically another piece of the puzzle, because what climatologists are doing is they take this data, they see what's going on, they can plot it onto these graphs, and then they look at different things to actually try to piece the puzzle together so that they can have a better picture of the whole thing. And they look for, checks and balances too. So, they might look at, for instance, a Greenland ice core, but they also might look at tree rings and see if they actually, match up and that they're telling them the same story so that they can, be completely confident in what's going on. All right, so this is going to be the Antarctic core record. This one is going to be going forward in time. So that's good, actually. It's a little bit less confusing. Okay, so let's see. You can see there's definitely... Oh, and so over here, this bottom one is going to be the temperature, the Antarctic temperature. And then up here, we're going to have carbon dioxide. Again, we can see the direct correlation between these two. Another interesting point that you can look at is how much more wiggly, I guess, this Arctic temperature gets, like the closer to the present that we get. And that's because we have better, tools to measure it with. We have better data points. We have more data points, actually. So it's a little bit more smoothed out over here because we have less data than we do in the closer to the present. Let's see. Also, because these ice core layers get more compressed as with the weight of the additional ice above it. And so as it gets compressed, then it actually gets a little bit more fuzzy as to the layers and how far back they actually are, to be able to date it, I guess I'm saying. And so that's another reason why this is going to be smoothed out a little bit more, and be a little bit more ragged, or whatever you want to call it over here. Okay, so we got the ocean sediment cores here. Now these can be used to study, sea surface temperature, ice extent, carbon dioxide, and ocean chemistry. These are used for quite a bit of things. Now the longest are from Ocean Drilling Project, and they go back as far as 200 million years. So we definitely have a couple of different things that go back quite a bit of time that we can use, like I said, to kind of cross-check each other. Now, these are actually going to be in these large areas here, same kind of idea. These are definitely file type of thing. They have these big cylinders that they drill out of the ocean, and then they put it into these big rooms. But these are going to be refrigerated. They're not going to be frozen. Let's see. These you're not going to see, as much like annual banding as you do with the ice cores. But let's see, and they look different depending on what's going on in the climate. So you can see here that they definitely look different depending on what's going on. This is not at all the same over here as it is over here. Another thing is you can see the glacial sediment deglaciation time periods by these, see this like kind of grayish area right here. That's going to be that glacial sediment. The glaciers are like moved, and they kind of just deposit sediment as it's going. Let's see, and then obviously deglaciation, is going to be the thing that deposits it. Okay, so this leads me to, what do you think is going on? What in the world is going on with those really sharp peaks and valleys in that Greenland ice core? Well, one of the things that scientists think is going on is going to be related to these Milankovitch cycles. Now, don't worry, I'm actually going to find a good video and post it for you guys that gives you a good animation as to what's going on with these 3 cycles. I definitely have taught this a few different times in another class, and it's difficult for me to kind of describe, when we get into the precession and obliquity. This one's a little bit easier, but I think it's going to be a lot better for you guys to actually visually see it when it's animated and moving than for me to try to describe it, because I struggle with describing that. So don't worry if you're kind of fuzzy about when I describe it here, because I just watched the video and hopefully it'll become a little bit more clear. Okay, but let's start with the closest point to the sun as being called the perihelion, and the furthest point is called the aphelion. So there's 3 Milankovitch cycles. This guy Milankovitch basically kind of figured out that there's cycles that the Earth goes through, with respect to its orbit and the way that it's tilted and things like that. So the first one is being eccentricity. So this is going to be the change in the Earth's orbit around the sun. It definitely goes in a cycle between being more circular and being more oval. Now, this actually gives quite a bit of ramification to the seasons. So when the eccentricity is low, there's little change throughout the year. You can see, if it's more of a circle, that there's going to be less of a change throughout the year than if it's actually going to be more oval, which is when eccentricity is high. And that means that the sunlight that's reaching the Earth is around 20% stronger. That perihelion, so at the closest point, okay, which is actually during the winter in the northern hemisphere. For those of you guys that don't know, the sun is the Earth is closest to the sun during the winter in the northern hemisphere. So these cycles, there's 2 cycles actually connected to eccentricity, and this is going to be a 100,000 year cycle and a 400,000 year cycle. So kind of cool. We can actually, plot it, look at it, and understand it. So something that I've had a lot of people mention to me that are climate deniers. How do you know that the Earth isn't just going through some secular, cycle that we're just unaware of? And we are aware of quite a bit of cycles actually that the sun goes through with sunspots, but also, as far as what's going on with the orbit and the Earth as well. Okay, so here's obliquity. This is going to be related to the Earth's tilt. I put some pictures down here just to kind of give you a visual reference, but again, I'll put the video here. I'll post it to Canvas. But this is where it's going to range from 28 around 21.8 degrees to 24.4. It does. This cycle is about 41,000 years. It allows when it's strong for a stronger summer sun and a weaker winter sun, especially at high latitudes. You can see here that if the tilt is going to tilt away, versus towards the sun more, then it definitely would affect the northern hemisphere there. Or at high latitudes, I'm sorry. And the ice ages often set in as the tilt decreases. So because the progressively cooler summers can't melt the past winter snow. So if you really think about it, if the summers are actually getting cooler, then when, winter goes into, spring happens and we get into summer, usually what happens is a lot of the snow melt will melt. But if it doesn't really get that warm, then that melting can't really happen, and it can easily put us into a glacier or an ice age. But on the flip side, that it can also bring the Earth out of an ice age. So say it's already like we have some glaciation going on, and the summers actually get warmer than they have been. So it's actually going to be able to bring it to where it's melting more. So that's good, right?